Okay, these are what I would call the six basic rules for integrals. They're the most popular ones that are just standard rules that you're going to see a lot. So we have power rule, exponentials, logs, cosine, sines, and inverse tangent. I will warn you that we don't see them very often with just x's. Most of the time they're used, and once you start getting used, meaning composite functions, everything starts to get a little more complicated. And I'll show you what I mean by that. But then certainly there will be a video called substitution. There's probably even going to be a U substitution part 1 and part 2 that you really want to look at. But these are the fundamentals. If you don't know these rules, I mean, it kind of is just the opposite of the derivative rules. So one would argue that if you know the derivative of e to the u is e to the u prime, then you know the antiderivative is going the other way, right? The derivative of a logarithm is 1 over u times u prime. So the antiderivative of du over u is the natural log. They go hand in hand. So let's look at some examples of each of these and we can kind of talk through. If we were going to use the power rule on something, it might be something as easy as, how about we just integrate, x cubed? Well, the integral of x cubed is increase the power by 1, divide by the new power. Right? So we can apply the power rule to a polynomial. We can apply it to a square root function. We can integrate the square root of x. Right? Increase the power by 1, divide by the new power. Dividing by 3/2 is multiplying by 2/3. Right? So our power rule, just like with derivatives, applies to all sorts of polynomials or square roots. We can integrate 1 over x cubed. Increase the power by 1, right? The power is -3, so increase the power by 1 makes it to negative second power, and then divide by that, which will make this a negative, and then we'll have to put a 2 in the denominator, right? Dividing by that is multiplying by half plus c. So we can use it for 1 over x cubed, 1 over x to the fifth, 1 over really anything, except we can't do 1 over x. We'll get to that in a second. But again, the standard rule for the power rule is increase the power by 1, divide by the new power, and we can use it for a variety of things. Okay, exponentials. We can integrate, e to the x. And it's kind of silly, but the integral of e to the x is e to the x, just like the derivative was. And here's what I said by we don't get the basics very often. How many times is it just e to the x? It's going to be like e to the 2x. So we're going to integrate e to the 2x dx. Well, that's going to cause a little problem, and we're going to, like I said, I'll talk about that in a future video. It's going to turn out that that's going to be 1/2 e to the 2x plus c, and you can think about where that half comes from. Same thing with logs. We can have easy ones, right? The derivative of a logarithm is du over u, or 1 over u times u prime, however you want to memorize it. And so logarithms are going to go the other way. Logarithms are great for like the integral of 1 over x. Well, we're going to get the natural log of x plus c. We can integrate 2 over x plus 3. That doesn't make it too much harder. That's just 2 times natural log of x plus 3. Right? Multiplying something on the top, adding something to the x. What happens is there's going to be a big difference if there's like the 2 over x squared or 2x or something, and then we have to change this. But again, in general, we're looking for a du over a u, a constant over a linear function, a quadratic function, some sort of relationship there, where we do the logarithms. Same thing when we have this 2 here, same thing we're going to get when we do cosine. If you just try to integrate cosine, well, that's easy, that's just sine. But if you do cosine of 2x, well, for the same reason, we're going to get 1/2 sine of 2x plus c. And like I said, we're gonna talk about that half in a future video. But certainly, you have to know the basics that the integral of cosine is sine, except we just have to worry about that factor. And again, think about the chain rule. If you took a derivative of this, you better get back this. And taking a derivative of sine of 2x gives you a cosine 2x times 2. 2 times 1/2 gives you that 1. Okay, same thing down here. It's nice and easy. The integral of sine is just a negative cosine. And then inverse tangent, again, it's not very often, but let's say we had 5 over, and the denominator was a nice, easy, just x squared plus 1. Well, then that is just 5. inverse tangent of x. Okay? And again, some of these are going to be nice and easy, just straight up inverse tangent. The 5 doesn't do much. Nice easy 1 over x, nice easy power rules. All the future ones, and again, this is going to be a really short video. The next video, u substitution, I'm really going to talk about then. How do you handle it when all these basic ones become true functions? Meaning, this isn't just x to the n. This is x squared plus 3x plus 1 to the 5th power. This is, well, cosine of x squared or cosine of 5x. This is, x squared plus 5 over 2x. We have to debate between maybe using those two. Okay? But the basics is just the rule. They're just the derivative rules in reverse. Power rule, exponentials, logs, inverse tangent, and then the trig functions. You have to know them pretty well. I mean, I could throw out any of the derivative rules, and you have to know them. Meaning, I could ask you for, what's the integral of secant squared? Well, you have to know that that's tangent. Because you know the derivative of tangent is secant squared. So then the integral of secant squared is tangent. You have to know the integral of, what if it was secant times tangent? Well, that's secant. Because the derivative of secant is secant tangent. So then the antiderivative of secant tangent is secant. I mean, all of the derivative rules you should review. So I'm not saying that these are the only 6. These 6 are the ones you're going to see the most. But every single one of your derivative rules you have to know in reverse. You have to know these fundamentals before you really try to attack any of the future u substitution problems, because the key to u substitution is that we're going to end up manipulating the harder problems to make it look like that. And once you get it to look like e to u to u, boom, the integral is e to the u. We're going to manipulate algebraically things and make u substitutions to make it sine u du. And once you get it to this form, you have to know the answer, because the answer then is just applying the basic rule. Okay? So kind of take a look at your derivative rules, rememorize them if you need to, but the integral rules are just the opposites.